So, in the last lecture I described the in situ polymerization analysis using diffusing wave spectroscopy analysis, and also I have shown you that how simple geometry based calculations can be used to find out the tortuous path which is traversed during that ink infiltration into the binder jet during the binder jet printing into the powder bed. Taking one step forward, I will be showing you that what is the time scale of the binder powder interactions. So, again we go back to the basic description of the avalanche of the binder droplets from the printer head, and this binder droplet essentially will be traversing into the powder bed, and this powder bed thickness is 80 to 100 micron. And if you see that what is the characteristic time, T star is nothing but T multiplied by V by D naught, where V is equal to velocity of droplet, and it is 2.5 meter per second, and average droplet diameter is 8.5 micron, and minimum residence time is 8.6 seconds. So, what you see that modified powder bed thickness that is based on our calculations, let us say 80 to 100 micron, and what you now can perceive that this when the binder infiltrates, this initiator, accelerator and monomer, they interact and they trigger the in situ polymerization reactions which form this kind of polymeric chains, and these polymeric chains essentially will hold the powder materials rather strongly, and it is more like a physical interactions, and physically these polymer chains will hold the binder will the powders very strongly, and that actually helps in the overall binding of the powder bed. Now, from the simple calculations of the T star is equal to T into V by D naught, one can find out that typical T star values, if it is 1.8 microsecond, it is more like initial impact. When time scale changes to more like 0.18 to 1.8 milliseconds, it is more capillary driven spreading. If it is more than 1.8 milliseconds to 8.6 seconds, it is equilibrium attainment. So, these are like some of the very basic description as how binder powder interactions takes place in real time. So, this is what I have already described to you, but what is the second point? First point is well taken. Second point is that if you add 2 gram of the initiator APS in 100 gram Ti6Al powder, then molarity of the initiator is like 0.54 molar. So, the propagation rate constant during the in situ polymerization of acrylamide addition polymerization is somewhere in K inverse is 130 seconds. So, the time scale of polymerization is order of magnitude higher than the equilibrium residence time, and therefore, would extend to a large number of layers and thereby trap the powder particles. What it essentially means is that what is the time scale of the acrylamide polymerization. So, this is the in situ polymerization, right. What is the inferences that one can draw from these simple mathematical calculations, because these mathematical calculations are important because those are used to validate some of the process science that we have discussed earlier. So, what I am trying to show you is that during this in situ polymerization, we wanted to know that when this APS initiator interacts with the accelerator and in the monomeric solution, when it will trigger the acrylamide addition polymerization, what is the time scale that this polymerization takes place. And from this what is found out, it is 130 seconds, and this 130 seconds is much higher than the equilibrium residence time. And what is the equilibrium residence time? It is of the order of few milliseconds. So, what it means that this infiltration or this polymerization will be not restricted to will not be restricted only to 2 layers, but will extend to multiple such layers. And this more the number of layers that this polymerization will be extended, more will be the ability of the ink to infiltrate and also to bind the powder particles. So, the efficacy of the binder infiltration, efficacy of the binding efficacy or the binding efficacy of the in situ polymerizable ink will be more and more if this binding takes place or if the polymerization addition polymerization extends to much higher time, so that it is able to extend to more layers. So, we will come back to the time scale of that overall time scale of the in situ time scale of binder infiltration in the powder bed. It is a kind of a summary slide, and as I have mentioned to you, this is based on the Washburn model, which is published in 1921, and this is a very long equations. What we are interested in this time scale of binder infiltration. All other physical parameters has been mentioned in this slide. So, what you see, it is avalanche of the binder particles, binder droplets which will come, which will essentially infiltrate into the powder bed, and this capillary channel, what is you can see in the blue ink region, this is what this binder infiltrates, and we can purely go through the simple geometric considerations. You can connect these 3 spheres and you make an equilateral triangle, and then you can find out that what is the different radius, and these different radius different scale or different length scale, and there you can find out that what is the time scale of infiltration. So, how to rationalize the in situ polymerization? Suppose if you have n number of powder layers. So, therefore, this glass shaped our glass shaped capillary elements are 2n minus 1 having the unit length of 2p. So, this one is a 2n and one is a 2p, and if you look at this, what is the total vertical capillary length of the nth layer of powder particle bed is 2p into 2n minus 1. And for the analysis of figures A and B, this is the figure number I am referring to, that now we are essentially extending our analysis not to 2 layers, but to nth layer. Then we can find out that effective diameter of the capillary is 4n divided by 4n minus 1 into p. So, as n increases, effective radius reduces, which goes well in line with the practical or whatever we have seen in practice. So, if you consider theta is equal to 0 degree contour triangle, which is not common, which is more for reference in hexane, and epsilon is equal to 0, the time required for droplets having diameter 45 micron, which we have measured using the shadowgraphy technique to infiltrate into a porous bed of having nearly 4 layers of particle, is 77.5 seconds. So, this is 77.5 seconds. In earlier analysis, we have found out the acrylamide addition polymerization rate constant is constant is 130 seconds. So, essentially what we are getting 77.5 seconds is much less than that of the polymerization reaction constant 130 seconds. So, since the time of penetration of the binder fluid into porous powder bed should be smaller than the size time of the in situ polymerization, this will allow binder fluid components to react with initiator mixed with the powder. So, these simple calculations essentially validates our theory of in situ polymerization as well as binder efficacy. So, once this 3D printing is over, we have used high temperature heat treatment, and then thereafter we have used microcomputer tomography analysis, which have been introduced to you earlier in one of the earlier lectures, to find out what is the 3D microstructure that develops. and also to do quantitative analysis. So, this is the as printed microstructure without any post binder jet printing, and we are getting volume fraction of porosity is 52 or 52% volume fraction porosity, and psi is 99.8%. That is the interconnectivity is 99.8%. When you do sintering and then after the as sintered microstructure you analyze, that volume fraction of porosity is 28% and interconnected porosity is 98.4%. So, the message that I am trying to send across, that post binder jet printing heat treatment reduces the porosity to a significant extent without causing much changes in the pore interconnectivity, which is hardly reduced from 99.8 to 98.4. And this is the number of pores. You can see this pore size. So, if you do this kind of distribution, you will see this is a large tail on the right handed tail, and this pore diameter is somewhere around kind of 10 to 12 micrometer. Now, if you see that number of pores here, you can see that this is also large long tail, and here again this pore diameter is almost of the same range, but the tail part is much more extended, and also there is a clear difference in the particle size distribution. Since the x axis scale is same, it is not the same, it is difficult to compare these two kind of size distribution. And this table essentially shows you what the number average pore diameter is. One case is around 9 micrometer, and in as sintered case, like after heat treatment, after the 3D printing, after the heat treatment, it is 12.5 micrometer. Now, we have measured the strength of these 3D printed structures, but the strength measurement was followed by strength reliability analysis. Now, what happens in the 3D printed structure, they have, as I mentioned in some of the earlier lecture, it contains microporosity. And also pores typically generated due to insufficient binder material interactions. And these pores, what is these pores? You have seen these pores kind of 10 to 12 micron. Now, these pores are essentially, when you do this 3-point bend test, for example, or 4-point bend test, so these pores are essentially distributed in the structure, right, in a random manner. So, larger the pores, more is the stress concentration. So, because it acts as a defect. So, larger the pores, more is the defect size. And that can essentially cause the failure of the materials. So, depending on whether this particular, depending on whether there is a porosity variation, if you consider this particular rectangular bar specimen contains that capital N number of small volume elements, you can consider this as a rectangular cross section samples. So, these porosity are randomly distributed. Okay. The volume element containing larger pores will fail fast. leading to failure of entire samples, right. So, this actually leads to a theory called weakest link fracture statistics. So, as I have mentioned earlier in previous lecture that it is not a material science course. So, I cannot cover all the elements of the material science, particularly on the mechanics aspect and microstructure aspect, but every now and then whenever it is required, I will explain to you in the simplest possible manner, so that you are able to follow and appreciate what I am trying to make you understand. So, this weakest link fracture statistics is more relevant for porous materials or for materials with defects, because the moment a material has defects, how these defects are distributed in the materials, that one cannot predict a priori, or that one cannot assume that how whether defects are uniformly distributed, and that is the most ideal case, but in most realistic cases defects are always randomly distributed in the materials. So, the microscopic region, what I am showing you, this microscopic region containing the critical defect size. Critical means in terms of sizes or in terms of the favorable orientation with respect to the loads that that particular microstructure element experiences under actual loading conditions, that those volume elements are most likely to fail fast, and if that microstructure element fails fast, that will lead to the failure of the entire sample. And that was the basic assumption or basic hypothesis on which weakest link fracture statistics was built, and then person who has essentially first proposed a scientist named Weibull, and that is why it is known as the Weibull's theory. Okay. So, this is in a sense this weakest link fracture statistics, and in the weakest link fracture statistics essentially is based on the probability theory. The probability theory is that survival probability of any volume element is equal to 1 minus failure probability, or failure probability of one volume element is essentially 1 minus survival probability. So, if this probability, if this total volume element comprises of capital N number of some, if the total sample comprises of capital N number of volume elements, each will have its distinct probability of failure, and when you do this complete failure probability of the total volume elements, then you can essentially put it as n number of volume elements, and then you can essentially find out that what is the failure probability, and if you do this failure probability calculations, this probability of failure as a function of fracture strength for this kind of 3D printed materials, and after the post processed like sintered 3D printed and sintered Ti6Al4V, we have taken 18 samples. So, larger the number of samples that you test under the 3-point bending, this is essentially used under flexural loading conditions, more is the good statistics. So, essentially if you plot this probability of failure fracture strength, it shows this kind of similar kind of curve, but if you take double logarithm of this 1 by 1 minus Pf, where Pf is the failure probability, if you plot as a function of the fracture strength, so you get almost like a linear variation. The slope of this linear variation will give you the Weibull constant 8.06, 8.1, and then sigma naught, this is a characteristic strength value, you get around 98.5 megapascal. So, just to show you this kind of materials has a Weibull modulus of 8.1, which is very close to that of the many brittle ceramics, because many of the brittle ceramics like alumina, their Weibull modulus is very low. So, like 3 or 4, if it goes to zirconia and all, it can improve, but Weibull modulus for many ceramics is not above 10. So, when the Ti6Al4b is metal, but it contains porosity and sufficient porosity, if you remember that these particular materials as a volume fraction of porosity around I think 0.48, as I have mentioned in the 0.28. Volume fraction of porosity 22.28, that means 28% porosity. If the Weibull modulus is 8.1, that is quite good, quite acceptable in this particular case. And this Ti6Al4b binder jet 3D printed in situ polymerized with using in situ polymerized binder. The compressive strength is more than 200 megapascal, and in also modulus is 4 gigapascal and Vickers hardness is 6.2 gigapascal. One of the things that we have done is that trying to find out that how the surface properties also change, because the surface roughness and surface properties are important, because that will govern the cell material interactions. And here in commercial Ti6Al4b average surface roughness is 0.1 micron, and whereas the SLM printed is 11.9 micron, whereas 3D inkjet printed materials we get is like 8.5 micron. And contact angle if you see in the SLM printed, it is around 60 degree, whereas in case of 3D printed and inkjet printed, it is more towards the hydrophobic side, it is like 85 degree, whereas in commercial 3D printed commercial Ti6Al4b, commercial essentially means this is the metallurgically processed, like conventionally processed. Metallurgically processed means this is like this is like either forged or rolled Ti6Al4v, and then what we get is like Ra value is 0.1 micron and contact angle is 51 degree. So, we have done some cytocompatibility analysis or cell compatibility analysis of these materials. We have used the fibroblasts, that is connective tissue cells, or osteoblasts, that is the bone forming cells, and this particular cell compatibility study was important because we are concerned about the use of, or people may show concern about the use of specific binder, and we have to be absolutely sure the use of binder, and if that actually remain there or if any residual binder in the 3D binder jet printed structure should not cause any negative impact or on the cell viability. And what we have found out that MC3T3 osteoblast cells are able to grow in a very linear manner from day 3 to day 7. DNA content also increases at different these 4 different materials. One is the control, this black box is the control, this is the commercial, that is metallurgically processed. This is like so essentially the commercial SLM, this is SLM selected laser melted, and this is the 3D binder jet printed structures. This is for the osteoblast cells and this is for the fibroblast cells, and you can see 3D inkjet powder printed structure has similar or even statistically higher number of cells compared to the control or metallurgically or the commercial samples. Now, when we have stained this fluorescently tacked and then we have used that fluorescence microscopy to image the cells which are adhering on the structure, these 3T3 fibroblast cells, if you see on the 3D printed structures, it very well spread. The same is true for the 3D inkjet printed structures for these materials when we have done these osteoblast cells, and this is the actin stained, and you can see MC3T3, that is osteoblast cells which are adhering on these materials. And when you do this fluorescence microscopy, if you see these blue stained regions, these are like nucleus of the cells. and other color features what you see apart from blue stain region, these are like cytoskeleton. So, what you can see clearly when the cells will adhere on this material surface, there is clear cytoskeletal reorganization that has taken place and which leads to good binding on that good cell adhesion and proliferation on these materials. So, this is that overview of what I have covered in last 2 lectures on the 3D binder jet printing of Ti6Al4V, and you can clearly see that I have shown you couple of features. One is the 3D microstructures, this is the 3D binder jet printer, and then and followed by sintering that leads to strength reliability of 8.1. It has volume percent porosity is 28%, and it also supports cytocompatibility without any compromise. So, this paper was published in Biomaterials in the year 2019, and you can see more details if you would like to follow this particular paper. And with this I close the scientific case study on binder jet 3D printing of the Ti6Al4V. Thank you.